So I'm going to review the third and final part of the module in this lecture. So we looked at computer science as an experimental technique. We looked at some more detailed linear algebra concepts involving matrices, and we looked at spectral methods and their application in computer science. As with the previous two review parts, I'm going to give some examples of typical questions. However, as also with the previous two review parts, I'm not going to go through the solutions to those. These feature as part of one of the tutorials. So we looked at, as I said, computing as an experimental discipline. So in particular, the exact nature of problems in computer science for which experiment is an appropriate technique. And this involved considering the basic statistical tools that we use and the ideas involved with those. So the notions such as a population, sampling from a population, probability distribution over a population. We looked at measures such as expectation, variance, and standard deviation, which are defined with respect to what I call the random variable taken from a population itself. I then looked at some very basic data analysis techniques, in particular this technique that's called linear regression and least squares fit. In matrix and spectral methods, we looked in more detail at matrix properties, so this idea of the determinant of a matrix, the inverse of a matrix. We introduced these notions of singular and non-singular matrices to characterize those matrices which have inverses and those which do not have inverses. I introduced the eigenvalue problem and how we analyze that and how that's defined. This very important result called the Perrin-Frobenius theorem. We looked at conditions which guarantee that the spectra of a matrix is consisting of entirely real values. Looked at some of the computational techniques for computing eigenvalues and eigenvectors, and finally reviewed three important areas in computer science where spectral methods are used. So in analyzing graph properties, in Google's PageRank algorithm, and in image compression. So statistical elements you have to know about, you have to be aware of. You should know what this idea of a population is describing, what it means to sample elements from a population, and this notion of a probability distribution. You should be aware of the difference between biased and unbiased sampling methods. You should be aware of what these measures of expectation, variance, and standard deviation, what they're actually describing, what they're trying to capture. You should know what exactly a random variable is doing. It's a function from a population to a set of real values, and why this is an important notion in statistics. You should also be aware of how standard deviation is estimated when we're working in real experimental contexts. And finally, the basic overall structure of how we carry out experiments by sampling and measuring members from a population. Once again, as with the case of calculus, you do not need to memorize formulae for, say, standard deviation, for variance and so on, you should look those up when you need them. So a typical sort of example question you might see, you're given some collection, say, of marks, and you're asked to state what is the median mark in that collection. You might be asked for the expected mark under the assumption that you're using an unbiased distribution. You might also be asked, however, for the expected mark under a given bias distribution. So the expected mark for this collection when we're using the distribution defined there. For data analysis, for regression, you need to be aware of what the framework and what the background to regression methods is. This formulation of best fit and how that's captured as an optimization problem. So this is this notion of least squares optimization as a way of finding the best fit line. You should at least be aware of the fact that there are various methods for describing optimization for regression techniques with different classes of functions and how those are treated as linear functions. You should be aware of methods for applying those techniques to data in practice, but you do not need to memorize formulae for describing the best fit line function. Once again, look those up. They're given in the slides, they're given in the textbook, they're given in the notes. Look those up if you need to. So again, a typical example question you might see, you're given a collection of data, a set of data values, a set of observation values, and you're asked to describe, to give the best fit line gradient for that data. For matrix methods, we went on to look at the operations of addition, of multiplying two matrices, of forming the transpose of a matrix. So you have to be aware of all of those. You need to know, again, what the concept of matrix determinant and matrix inverse are capturing. You need to be aware of the distinction between singular matrices and non-singular matrices, those which have inverses and those which don't have inverses defined. You should be aware of the basic conditions that guarantee a matrix is singular. You don't need to memorize formulae and algorithms for computing inverses or determinants. Once again, if you need those, you should look those up. In spectral methods, you need to know what exactly the concept of eigenvalue and eigenvector are describing. So what the form of the eigenvalue problem, as I called it, is. You need to be aware of conditions which ensure there's a dominant eigenvalue in the case where all of the eigenvalues in the spectrum are real numbers. You should have some awareness of basic computational techniques. So I described the power method as one way of finding eigenvectors for a matrix which has a dominant eigenvalue. You also need to be aware of the background to important applications. Again, typical example questions you might see, you might be given a number of matrices and you're asked to say which of those matrices is singular, which of those matrices is non-singular. You may be given a collection of statements, some of which are true, some of which are false, and asked to decide between them. So for example, these four statements, two of those statements are always true, two of those statements are sometimes false. Example questions you may see with regard to spectral methods, you may be asked if you have a value 0 is an eigenvalue of a matrix, then there are certain properties you can deduce of that matrix. So what are those properties? You may be asked using the power method to find the eigenvalue of a particular matrix. So that matrix below. So you should make sure you know how to apply the power method to a given matrix. You are perfectly free, obviously, to use calculators to assist in that calculation.